Right, well, good afternoon, everyone, and welcome to our webinar today. I'm going to talk a little bit while people are trickling in still. The Engineering Integrity Society, very brief intro for anyone who's not particularly familiar with us. We're a not-for-profit organisation drawing engineers together across the UK and indeed some of Europe. To share experience and advance our professional development, discussing aspects of durability and fatigue and testing, all that good stuff. We run moderately regular webinars, some like this, particularly targeting useful information for younger engineers, new people to the profession. We have discussion, we have more focused groups, you can see up on the screen at the moment, with different aspects of the work that we're interested in, and we do from time to time do full seminar days or series of seminars on different topics. Looking at the time, come on to the next slide. Thank you, Sarah. I should just draw your attention to a few future events. One is our annual exhibition. Often that's a little bit earlier in the year, but that's in May this year. That's on instrumentation, analysis and testing. So we have an exhibition of people supplying all sorts of different stuff there. And we also run some discussion series. We've also got more young engineers forums during the year. We have a event probably mid-year, which is going to be announced soon, talking about repeatability, reproducibility, and uncertainty of measurement, which is certainly it's a perennial topic, and it seems to be something of heightened interest of recently. That's more than enough of me talking. Our speaker today is Anton from Vishay Measurement Group, Anton Chittey, who you can see here. He's going to be talking to us about strain gauge technology and how prevalent it is, some of the pros and cons on different aspects of it. Anton has worked with strain gauges for over 30 years now, and on all sorts of applications, some of them more conventional sensors, some of them quite unusual and novel instrumentation jobs. I think the best thing is for me to hand over to Anton to give his presentation. I'm just going to highlight a couple of things. We're going to go through the presentation with microphones off, please. If you do have any urgent clarifications, please put them in the chat box, and I will try to interrupt at a reasonable juncture. When we get to the end, then I will sort of coordinate and MC the questions. If you'd like to put a question in there, I'll read it out. If you'd like to give an indication that you want to ask it directly, again, flag it up in the chat box, and then I can call you out and I invite you to speak. So with that in mind, without further ado, Anton, over to you.
Okay, thank you very much, Peter. I'll just load up my slideshow and we'll make a start on this presentation. So here we go. Right, yeah, so we're the Young Engineers Forum here. So my start is the title slide, as you've seen, which is that strain gauges are pretty well literally everywhere, and I'm interested at the end of this presentation whether you can come up with your industries that we don't cover in this presentation. Now, I will add that putting this together has been more about what I don't include rather than what I do, so it cannot possibly include within our 45 minutes everything. I just want to review very briefly who we are as a company, because I know some people who know of us get confused as to who Micromeasurements are, who VPG are. So I'm just going to give you a very brief overview. So firstly, VPG essentially is a foil technology company. And obviously today we're talking mainly about strain gauges, But you can't avoid, when you talk about strain gauges, talk about load measurement as well. The foil also goes into making very high precision resistors. Obviously, the strain gauge going to our load cells, and we produce systems with load cells, which can be process weighing, that kind of thing. And we also have other brands as well, including instrumentation companies that can do 8,000 plus channel systems. We have the ultra miniature DTS brand on board now. We also have Dynamic Systems, a thing called a Global, which is to make and evaluate different metals. And there's a few others as well. So if you want to see more of what VPG do, there is a corporate website. There'll be copies of these slides a bit later. Micromeasurements is a brand of VPG, and we are primarily a strain gauge company. And you'll often hear about advanced sensors technology. And I'll just make a couple of comments about that throughout this slideshow. We do all the accessories in order to properly bond, wire and protect a strain gauge. So that's a one-stop shop. We provide the instrumentation. We can also bond strain gauges to your own hardware, both on-site and in our Basingstoke office. And of course, training workshops. So this presentation involves some of the slides that we do in our own hands-on workshops. And so it really comes down to the company that I'm employed by, Vishay Measurements Group UK Limited, and we represent obviously the Micromeasurements brand, the strain gauges, VPG transducers, foil resistors, and Pacific Instruments. And we've been in Basingstoke for more than 30 years, and in fact, we photo of the building there. I've been working in that building for more than 30 years, so been around a long time. So that's just a summary of who we are and what we represent. So it's mostly strain gauge. So really starting off with the points of this presentation, we really should start off with what is strain. So some really simple slides here. So this is from first principles. Strain is a change of dimension or shape. So there's some physical change, and it's described in engineering terms as change of length over original length, and is represented by the symbol epsilon, as you can see here. Now, it should be obvious to say that if we had a change of length that was the same as the original length, so let's use an example. If we had 100 millimeter length and we stretched this by a further 100 millimeters, we would have one strain. Now, one strain, obviously most materials don't go to one strain, so we often talk about microstrain, which is invisible. Okay, we can literally measure the invisible. So we're talking about one microstrain, which is 0.000001 units per unit, whether that's meters per meter, inches per inch. If you think of a meter rule, 1 micron in a meter is 1 microstrain, so micron being a millionth of a meter. And if you actually calculate that down to work out that 1 micron in a meter, what that does on a typical 6 millimeter gauge, we are talking about measuring 6 nanometer changes. And that only becomes apparent how small that is when you consider the wavelength of visible light is between 400 and 700 nanometers. So we are essentially measuring things that are 2 orders of magnitude shorter than we could see really in any sort of visual system. And if you think of this 6 nanometer on a 6 mil gauge, if we have a 1 millimeter gauge, we're measuring 1 nanometer changes. Now, if that doesn't quite compute in your brains, then let's do another comparison. So this is a picture of, well, many of you will recognize hopefully the UNESCO World Heritage Bridge, the 4th Rail Bridge, the 4th Road Bridge, and then the new Queensferry crossing. Now, this bridge is 2.7 kilometers long, and 1 microstrain is equivalent of a 2.7 millimeter change in the length of that bridge. So, you know, as I put here, a typical iPhone 12, 7.4 millimeters thick. So it's half the thickness of your mobile phone in 2.5 kilometers. We're measuring that consistently, reliably, and in many cases, we can actually return to better than 1 microstrain. So that's a comparison of what we're actually trying to measure. So then the obvious question, what does a strain gauge measure? Well, it measures, as the description says, strain. So just click the mouse there. Strain, it's a simple answer to a simple question, but we also get many questions about measuring different values with a strain gauge, but strain gauge cannot and do not measure stress or pressure, displacement, all these things that I've listed here. You may require a transducer if you want to measure pressure or load. So if you're trying to measure kilos, you cannot buy a strain gauge to measure 20 kilos. You can, however, buy a load cell to measure 20 kilos that happens to use strain gauges. So this is just a few pictures here showing typical point of sale weigh scale, perhaps a torsion measurement in a drive shaft, perhaps a silo weighing system. These are all strain gauge based measurement devices. So the strain gauge cannot measure directly these, but indirectly the strain that they detect can be calibrated in the units of choice. So I mentioned stress as well, so we should just briefly cover stress definition because people often talk about stress and strain as being the same thing, and in engineering they are distinctly different. So stress is the internal pressure due to the load on something. So this force now, rather than showing the strain, we are showing that this force over this cross-sectional area gives us this pressure measurement, and it's defined with the Greek letter sigma is force divided by area. You cannot put a pressure transducer into a solid, so you can't actually measure that pressure directly. You'll talk about the units of pascals or pounds per square inch, that kind of units. You can calculate the stress because stress is proportional to strain and Hooke's law, which many of you would have done at school or college or university. So we measure strain, we can then calculate the stress if we know the material properties. So we have a strain gauge measuring strain, we use that to calibrate in whatever units we wish. So what does a strain gauge look like? So let's look at the construction of a strain gauge. And it's pretty simple. We have a thin resistor. Okay, I'll put in the very thin in there. We'll come to that in a minute. We've got a foil on some sort of non-conductive backing. Somewhere around 25 to 70 microns. It does depend on the actual gauge type. Some are thinner, some are thicker. This will be considered a typical range. These sensors are bonded to a structure using some process that we will review very briefly. And this will accurately follow the structure's deformations, and it will give you a resistance change as the strain changes. Just a bit more of a close-up here, and there's a few more bits of terminology, and I don't really have time to go through all of these. I've been timing this, but you can look at this at your leisure at a later time. This just shows another close-up with some of the terminology. We have here the gauge length. So when we talk about a 6mm strain gauge, we mean that the length inside these end loops here is 6mm. And the strain measures average strain in the grid, and it measures strain in the direction of the grid lines. And that's why we have these very distinctive alignment marks, so we can position the gauge accurately to take the measurement that we wish to take. When we say very thin, let's define the two things it's made of. Well, the foil, we talk about 5 microns, although we are rolling foil down to 2.5 microns on occasion. And the matrix, typically 25 microns. It can be thinner with some strain gauges, thicker on others. But we are talking about a device that is something like half the thickness of a human hair overall. So a typical human hair is around 50 microns. The foil is 1/10 of that, and the matrix is half of that. So it's a very, very thin sensor. One thing to note, by the way, this is a traditional strain gauge. Notice that they have this serpentine pattern with the end loops, and we'll contrast that to what we call the advanced sensor in a little while. Now this strain gauge is a photo etch device. So we take a foil, bond it to a carrier, and then we photo etch a pattern. So they can be photo etched in many different patterns. Now I've been saying for 30 years that we do 250,000 different types of strain gauge, and we produce new patterns, custom patterns every week. So it's certainly well over now 250,000 different patterns. We can have what's called a single linear strain gauge, designed to measure strain in one direction. We can measure torsion or shear, so you might want to do convert a drive shaft to torsion measurement for power output. If you want to measure a linear strain gauge, you need to know which direction to put the gauge. whereas if you use a three-element rosette, you can resolve by maths the actual principal magnitudes and directions. So if you don't know direction, a three-element rosette is ideal. We have T-rosettes, great for material property testing that I'll mention a bit later on. And we also do residual stress gauges, where you drill a hole and measure the change of strain to the relief of stress, and then you can calculate the stress that was in the part before you drilled the hole. We also do a range of weldable strain gauges that we'll mention later, and the grid sizes can be anywhere from 0.2 millimeters up to over 100 millimeters. This is because a strain gauge is an averaging device. If we're working on concrete, we want to get an average strain in the concrete and not a local strain on or near one of the lumps of aggregate. So there's many thousands of different patterns that you can choose from to suit the application. Let's move on to strain gauge performance. So we know what a strain gauge looks like. How does it perform? So the first obvious thing we should think about is, we talked about it being a resistor. So common resistances, I'm not going to go through all of them, but we got typically 120 ohms, which is traditionally the resistance that you would have seen. But 350 really is the most common if you're doing general stress analysis, or if you're building a load cell. Most commercial load cells will be 350 ohms. We're using more and more 1000 ohm strain gauges simply because of battery power, so you'll preserve your battery life better with a 1000 ohm gauge. And we're doing more and more 5000 ohm gauges. They're becoming easier and easier to manufacture, particularly with our advanced sensor technology. Now, many people look at this strain gauge here and wonder why there are discontinuities in the etching. These are not, these are little circuits that can be added to the resistance by laser etching. So rather than traditionally a gauge would be abraded or chemically etched to achieve its target resistance, these are actually laser etched nowadays. So this is the advanced sensor technology unique to us as a manufacturer. There's other resistances in here as well, 175, 2000, 10,000. So we can do pretty well any resistance that you desire if there's a custom requirement. So we mentioned the strain gauge is measuring strain, and we want to find out the sensitivity or calibration factor of the gauge. And this is done statistically through an ASTM test standard, where we bond the gauge to a special beam, we apply a known strain, and we measure the resistance change. So this gauge factor, the thing we're interested in, is a function of the change of resistance versus the original resistance over the change of length over the length. And of course, this is a microstrain, or strictly it's strain in this equation. So if we apply a known value here, we measure the value here, we can calculate gauge factor. And this is a statistical number that comes with the gauges that you purchase. Gauges are also sensitive to thermal effects. Now, it sounds like a disadvantage, but actually this is an advantage in many measurement situations. This thermal output can be used to measure things like expansion coefficient. But if you take a gauge and you bond it to the material for which it was intended, you will get this very strange S-shaped curve. But the great thing about this is, around room temperature, it's virtually flat. So if you're doing laboratory tests, you will have no thermal output or no measurable thermal output. If you do happen to change temperature, let's say to 100 degrees Celsius, you can see here we're somewhere around minus 90 microstrain, and this curve is published with every pack of gauges. So you can actually know, you can plot this in an Excel spreadsheet or in your instrumentation to automatic correction. And as you would expect, every pack of gauges comes with this engineering data sheet. And this contains information we just talked about. So it contains gauge factors. Now in this case, it's a 3-element rosette. So I've got 3 gauge factors listed. I mentioned nominally 2, but you often find these will be 2 point something. Some are down 1.8, 1.9 something. So it depends specific on the pack of gauges you've purchased. We've got the grid resistance here with its tolerance. We've got the numbers that will be plugged into a polynomial to give you the thermal output curve that I just described. And there's some other information here as well that I won't go into. Again, we don't have time to go into every detail. But one of the great things with this is it has a 2-dimensional barcode which contains all of the information in this data sheet. So you can zap this into a spreadsheet or a report, or you can plug it into, if you're using our software, we actually take this straight into our software for optimum data. So that's what a strain gauge looks like, how it performs. We obviously need to install it. So every gauge comes in a pack, clean and ready to install. And I'm just going to go through this briefly because we do a 2-day strain gauge course for bonding strain gauges. We're going to review it in about 5 minutes. So let's go through the short process. So the first process is preparing the surface that you're going to bond to. And we want to bond the gauge to the material that we want to measure on, not to some superficial surface. So we're going to abrade back to base metal. We're going to provide some sort of marking out so we know exactly what position to put the gauge. We're going to follow that with some chemical cleaning. Some materials use an acidic etcher, very mild phosphoric acid. Perhaps use some sort of degreaser, avoid acetone or degreases that leave a residue. And then we make sure that we reach neutral pH on the surface as well. So if you use an acidic conditioner, you must use a neutralizer for optimum pH for letting the adhesive bond to the surface. So that's preparing the surface. Next process is you have a gauge and you want to position it on your alignment marks. First thing is we use a gauge handling tape and we use high quality mylar that is extremely stretch resistant. So we position it and then we get the adhesive. Depending on type of adhesive, you may need to mix it. If you mix it, most mixed adhesives have a limited pot life, anywhere between 15 minutes and 12 weeks, depending on the specific type of adhesive. And then you would apply it to the gauge and the surface according to the instructions. And some adhesives will require clamping and heat curing. If you're using an instant adhesive, it might be 1 minute sun pressure. If you're using one of the heat cure adhesives, it might be 2 hours in an oven, for example. Once you've completed that cure process, the next stage is to start attaching lead wires. Now, many gauges come with lead wires already attached, but there is no doubt it's better to bond the gauge first, then solder the leads on. You get much better results. If you use solder, you must clean the flux residue thoroughly, and you would then go on to test the installation. And these 3 basic tests are essential. We have installed resistance. Have you managed to damage the gauge, or have you mis-soldered it or shorted it out? We have the insulation resistance. The gauge should be isolated from the surface. And these 2 tests, we use our little Model 1300 gauge insulation tester. These buttons here actually are in percentage deviation. Zero return, you can use a strain indicator, something like our P3 or other instrument, and that enables you to apply a small load and make sure the strain gauge return to 0. This is assuming the structure they're bonded to returns to 0. If you're happy at this stage, you can go ahead and provide some protective coating to make sure that installation is protected from the environment that it's going to be in. And of course, you should then retest the installation the same way as we just did to make sure you didn't damage the gauge during applying the protective coating. From that point, you can actually start taking data. Now, before we move on to that, we're just going to review some of the products we use. We talk about using strain gauge certified products. We do more than 20 adhesives, for example. The most common that some of you will already be familiar with is instant adhesives or cyanoacrylate style adhesives. We produce M-Bond 200, which is a strain gauge certified adhesive. It's designed to go off in thin film. It doesn't have the plasticizers and fillers that are typical of high street cyanoacrylates. So don't be tempted to use a generic adhesive. Do use a strain gauge certified cyanoacrylate. We have cold cure adhesives. So 100% solid epoxies, for example, are really good for long term. They're moisture resistant and they're good at gap filling and textured surfaces. So you can bond to concrete, rocks, pre-preg composites, that kind of thing. They will fill those gaps, whereas a cyanoacrylate will not fill the gaps. And then if you want the ultimate performance, heat cure adhesives, something like M-Bond 610, almost every commercial load cell you purchase will be using this adhesive to hold the gauges down. 30 plus years, in fact one of our divisions has now got an MTBF of 50 years using our strain gauge as an adhesive. So really good if you want the widest temperature range, the longest life, -269 to about +370, so very wide ranging temperature as well. Used a lot in superconducting magnet and type applications for that cryogenic capability. And then protective coatings, again, I'm not going to go through all 20, but you might have a laboratory environment where you just want to paint something over the top of the gauge. You might have a field application, so out on a bridge, you want to put some coating down to protect against wind, rain, snow, that kind of thing. Or perhaps you're building a transducer that's got to work in a supermarket, and again, there's different coatings that will protect it there as well. So we can guide you on all these protective coatings. There's many, many choices. These silicon rubbers are often the choice. Something like M-Coat 3145 is a single component, corrosion-free silicon rubber. Don't be tempted to use something that you would use in your bathroom. It must be corrosion-free. So that's just a review of some of the products that are used in conjunction with strain gauges. So let's move on to taking measurements from the strain gauges. And the first thing we need to know is we've talked about the gauge factor. What does that mean in terms of the measurement? So the first thing is we'll do a simple formula, and this is a rearrangement of the gauge factor formula. So we have our change of resistance now that we're interested in, which is equal to the gauge factor times the strain times the start resistance. Gauge factor normally with 2, 1 microstrain or 0.000001 times 350. So we have a change per microstrain, in this case, of 0.7 of a milliohm. Now, I talk about measuring the invisible with the undetectable. So that's where we are. So how do we take this invisible measurement that produces an almost undetectable resistance change? Well, I'm sure many of you recognise the Wheatstone bridge. And there we have Sir Charles Wheatstone, the guy who didn't invent it. A guy called Christie invented it. Sir Charles Wheatstone did give a nod to Christie, but he was a bit of a rogue, and I think he got his name put on it. But anyway, I digress. Essentially, this is a balancing circuit. And so if I move on a slide, I would liken it to your traditional kitchen balance, where if R1 and R2 are the same value, so liken them to the same size of this weigh scale. If they have the same value, the pointer here will be pointing to 0. Equally, if these two are the same, this point here will be at 0, or halfway between the excitation voltage. Of course, if R3 and R4 are the same value, it will also be true this side as well, and therefore I'll have no output from the bridge. If I introduce an imbalance in one or more arms, then I will get a change of output. And this particular diagram shows what we would call a full bridge. You'd have one or more strain gauges in each of these arms, and this would be something like a commercial load cell. So all commercial load cells use full bridges, active resistors or strain gauges in each arm. For general stress analysis, we use quarter bridge. In other words, one of the 4 resistors is a strain gauge. The other 3 are backing the instrument. And I've just brought up one little addition here that I don't normally talk about, but we've got R1 and R2. If they're the same value, this point is at 0. If R3, often called the dummy resistor, is the same as RG, the strain gauge resistance, then I'll have balance. Also, the resistance of the lead wires, so small R1 and R2, if they're equal as well, the bridge will be balanced. And I've just added in here, R3 plus R1 is the same as RG plus R2. Now, this third wire, the so-called 3-wire cord, this third wire doesn't have any effect on the output because this readout here is maybe many megohms, so we could ignore any resistance here. But the great thing about a 3-wire quarter bridge is the bridge remains balanced no matter what the length of the lead wire. It also remains balanced if there's a small temperature change in the lead wire, because copper is a very good temperature sensor. So any delta R will be equal in these two as well, and it will balance out. This is the typical 3-wire quarter bridge. So with this circuit, we can calibrate it, and one of the ways to calibrate it is to use a thing called shunt calibration. Again, any of you who've done electronics will know, of course, the simple calculation for resistors in parallel. And there's a complete calculation here to convert that change of resistance into microstrain. And let's say I choose our cal to equal 1000 microstrain. So I will close the switch, resistance change will be equivalent of 1000 microstrain. Now this particular 3-wire circuit, R1 would cause this value to be slightly lower than you would expect. R2 would cause the same desensitization to the strain gauge, and therefore when I throw this switch, if this doesn't read 1000 microstrain here, I can boost the gain to read 1000 and automatically compensate for the lead wire resistance. And that's really good if you're working on something like a bridge. You might have maybe 50, 100 meter leads. The shunt cal circuit can enable you to automatically correct for that lead wire desensitization. And in digital instrumentation, you press a button and it does the calculation for you. A lot of what we talk about with instrumentation is talking about using dedicated instruments. So although you can go to first principles and build something yourself, dedicated instruments do all of this for you. So they generally include the bridge completion, the shunt calibration circuits with the maths to cope with that. Variable bridge excitation, again, don't have time to go into it in detail, but a small gauge on a plastic or composite would heat up a lot more than if you had a large gauge on a piece of aluminium. And so you might need some variable bridge excitation in your instrumentation. Again, beyond the scope of this lecture, but anti-alias filtering is essential, particularly because almost every instrument now is digital, and so you've got some sort of HD converter. You then would calibrate that in some sort of engineering units, and then you would apply some error correction. And again, the datasheet that I showed you earlier has some additional information, and if you plug that into your instrument, you can make some error corrections. Now, in this particular slide, I do like this picture here. This is actually a picture of Dr. Felix Zandman, the guy who started the company back in the 60s. The maths he's doing there has nothing to do with what we're talking about, but I just like the fact that he's the guy who started all of this. So having reviewed the entire process from what a strain gauge is, or what strain is, all the way through to taking readings using Wheatstone bridge and all the things that go with it, I want to move on to real-world applications. This is a little bit of an out-of-date graphic, but I quite liked it because it showed that, you know, things like the lunar lander, the touchdown, was measured with a strain gauge. Concorde, yes, okay, maiden flight in '69, still looks futuristic now. Yes, maybe automotive technology has come a little way since vehicles like this, but I quite like that graphic for that reason. It shows a bit of history. So let's start at the really basic end, so kitchen and bathroom scales. And again, this is where maybe people don't realize there are strain gauges literally everywhere. So if you're at home, you're baking a cake, you might have a weigh scale, which might use one very small central load cell underneath the weighing pan, generally pretty low cost. Bathroom scale often will use 4 miniature load cell, one under each of the 4 legs. And generally these are low cost, and we can therefore suggest that they are low accuracy. That's not to say they're low resolution, because you might be apparently measuring to 1 gram, but the overall accurate measurement is going to be relatively low. A typical weigh scale, I think, from a supermarket is maybe £20 or less, so very low cost. If we talk about retail, generally the costs are a little bit higher. So we talk about loose product pricing. You want to buy your apples or whatever, you place them on the weigh scale and it gives you a price for them. And then there's the bane of everybody's life, the unexpected item in bagging area. It's a constant problem. So you scan your 5 kilo bag of potatoes and your bag of crisps, and every one of those things is weighed as you put them on the scale. A pain that I have is my kids like to help me, so they will hold the handles of the bag whilst you're trying to pack. And of course, the load cell can actually feel that somebody's holding the bag. So you can blame that on strain gauges. These are generally very high accuracy. They have to reach at least 0.03% overall accuracy. And of course, they're higher cost because of that. Perhaps you don't know that strain gauges are used in actual food production all the way to the farmyard. So we do pins for measuring ploughing depth and seed planting depth, all done by force measurement. Anti-jamming mechanisms for combine harvesters. They also may have a grain yield deflection plate. So the grain is fired at the plate, a load cell measures the yield per unit area, and then the farmer can make judgments about where in the field he needs to perhaps put more fertilizer. And then that grain goes into a silo. Silos are often mounted on load cells, and so they can tell how much grain is in the silo. Also used in factories. So your loaf of bread may well have been made in a massive vat, and that vat was mounted on load cells. So you put a ton of flour in, and it's controlled with strain gauge based load cells. You may also not be aware that even milk is weighed, and they can actually work out the yield per cow. So it can indicate whether the cow is suffering from some sort of a medical problem. And again, something that everybody will be familiar with, packaging by weight, not volume. The contents may have settled during transit because they're all weighed. Your cereal is weighed into the box. Transportation. So automotive applications, okay, hopefully none of us see this, but of course strain gauge would have been used to test these crash resistance of your car. They would have been used on wheels, tyres, suspension components, drive shafts, the glass, the bodywork. Pretty well everything that you can think of would have been tested with strain gauges. If you're a keen cyclist, I'm a mountain biker myself, but if you're a road cyclist, often people want to measure their power output, and there are many strain gauge systems that get integrated into pedals, the spider, for measuring power output. Trucks, lorry weighing, so this could be for optimally placing your load in the truck and making sure you don't overload it, which can be a legal problem. And it could be integrated load cells like these or sensors applied to various strategic points in the vehicle. Trains, the rolling stock and the rails themselves may have strain gauges on. So rails with strain gauge on can measure wheel flats on the rolling stock and also can be used to measure the train as it goes over an instrumented section of track. And then ships, very commonly measuring power output on ships' drive shafts. But of course, the entire ship superstructure can be tested. We've tested pylons. We used to do deck displacement measurements. So again, strain gauge all over ships as well. Perhaps someone you shouldn't be too surprised that strain gauge used in the aerospace industry extensively. And in fact, the strain gauge has a parallel history with aerospace in terms of its development. In fact, foil gauges were invented by Saunders Roe on the Isle of Wight back in the 50s. So let's start at the beginning. So material properties. Now, I don't have a specific slide on material properties. Perhaps I should have done, but this is where you would take your piece of material, you put it into something like an Instron test machine. That test machine applies a load to a strain gauge based transducer, and Instron do use all our strain gauges in their load cells. You then have a coupon with a strain gauge on it, and you get load versus strain. If you measure the cross-section area, you can now calculate the properties of that material. This just happens to show a shear modulus V0 specimen, a Joseph Pescu specimen. Component tests are measuring bits of undercarriage or specific joints in aircraft. Full-scale fatigue tests. You can find some nice YouTube videos on fatigue tests on aircraft. Perhaps they're testing a whole wing or even the entire aircraft itself. Active joysticks measure force, not displacement, and they're all strain gauge based. So if you've got fly-by-wire, you may well have strain gauges on the joystick. Health usage monitoring systems. So this is where strain gauge are mounted directly on the airframe, so you can do predictive maintenance based on what sort of life that particular aircraft saw, whether it saw battle or whether it just saw nice, clear air and gentle turns. And something like F-35 is covered in strain gauges in production. You might be looking at launch forces. So if you've got some delicate instrumentation on the rocket, you might want to know what forces that's going to undergo during that process. Also robotics, and in fact one of the Mars rovers has some of our strain gauge based load cells on the arm to measure forces. Not easy to repair something that goes wrong on Mars, so we measure force on the robotic arms there. Then we can go to the really basics, of course. When you go on holiday, your baggage is weighed. Strain gauge based load cell again. You also may be surprised to know that sometimes they weigh the entire aircraft as well to look at things like centre of gravity, which is important for flight safety. It could be a roll-on platform like this, or it could be jacks with load cell built into them. Safety, there's many safety systems that some of us will be familiar with. So overload is an obvious one. You don't want to break your crane. Lifts, if you've ever been unfortunately crammed into a lift and the doors refuse to close, and then you notice the little sign that says maximum 8 people, well, there's a load cell in there towing the lift. There's too many people. Also transport, we mentioned about trucks, and of course that could be overloading from a legal point of view, or just simply safety. If the truck's overloaded, it can damage the truck or cause a crash. telehandlers for tipping, so you're measuring centre of gravity and predicting when you're going to a point where it's unsafe. And then you've got robots and cobots. Now, control feedback and force feedback, more importantly, is really useful because you really don't want the robot to crush this person's hand. So safety criticality means that strain gauge has to be put into these robots, particularly if they're working alongside human beings, who tend to be quite breakable, unfortunately. Let's look at some specifics. Now, I mentioned the Queensferry crossing earlier. And again, this bridge here, and I was fortunate enough to be working on this bridge many, many years ago. So there's more than 1,000 of our weldable strain gauges on the structure. And they're weldable because you need to be able to install gauges really any time of the year, whether it's raining, snowing, icy, or whether in that rare occurrence of good weather in Scotland, you need to be able to weld these on. And you use a portable capacitive discharge spot welder, something like this. This happens to use a lithium-ion battery pack, so you can carry this around with you. And this is for what's called structural health monitoring, or SHM. And it can be used for measuring construction forces, life cycle prediction, and preventative maintenance. So for construction forces, the Queensferry crossing has the world record for the longest unsupported cantilever. I think it was something like 680 metres. You can look at the Queensferry crossing website for some of those statistics. The preventative maintenance is an interesting one because whilst they were building this bridge, the Forth Road Bridge had to be closed because a crack was found on it, and the strain gauge team from here went over to that bridge and did some more testing to see whether the bridge was safe or not. And within 6 weeks they managed to reopen it, but they made recommendations for what the ongoing maintenance needed to be to make it safe for a lot longer. And one of my favourite trips in my job over many years was to go to the top of the North Tower here. They were still pouring the concrete. We were about at 180 metre level. And it's quite surprising to be outside and looking down on what was one of the world's biggest bridges. It's quite a sight. You're probably surprised to know that strain gauges are all over mobile phones as well. I think if there's anybody in the audience without a mobile phone, I'll be very surprised. So the first thing is that we use strain gauges to measure the manufacturing strains. So one of my jobs is going all over Europe and teaching people to bond strain gauges, PCBAs, to basically validate a production line. And that production line can't start manufacturing these PCBAs until it's been shown that they won't exceed a certain value of microstrain as a standard for that testing. You may also be surprised to know, of course, that if you ever drop your mobile phone, you pick it up and it's still working. So you can thank this standard here, which is the drop test method for handheld electronics. So again, this is a strain gauge based test to improve the reliability of your mobile phone. More and more now you're seeing integrated strain gauges. There is a phone on the market with squeeze control, so the person will squeeze their fingers in a variety of different ways to make different actions on the phone, and also haptics, so not only where you press but how hard you press. So some products have a strain gauge frame with the screen mounted on it, so actually measure the force directly. And then there are a few patents that are going to start talking about integrating strain gauges into the structure of the phone, and there'll be a little recording circuit in there. So if you drop it, it will detect their 0G and start recording. So you go back to the shop to claim your phone broke whilst you're making a call, but the recording of the phone will tell you that you did drop it. So it could be a warranty issue. And then some of the more surprising things that I've seen over the years is paleobiology. And this is where people are trying to compare ancient and modern skeletons to tell something about the ancient skeletons. And so strain gauges are bonded onto various bits of modern skulls and bones to improve the digital twins, the computer models, and then they can actually use that to find out maybe how a dinosaur walked. It's quite a fascinating area. There's a sample paper there again. When Sarah shares this slideshow, you can click on that link. I picked this particular paper because I trained somebody in our strain gauges and systems many years ago, and she turned up on a program being interviewed by David Attenborough about a particular dinosaur bone. And I helped train her with strain gauges, and this paper refers back to our digital systems and our strain gauges, so you see our information in that paper. And the biomedical side, and again, something I find fascinating, somewhere that, you know, is so far out there in terms of where you think strain gauge might have been used or might have imagined they being used. I've been involved for many years in mitral valve repair rings, where a rapid prototype printed ring will be strain gauged and then sutured into a heart, and the force is measured whilst that heart is beating. It's to optimize the design of these rings. And the guy that I did the original research with, we wrote a paper together, which you'll find on our website. The rings now are saddle shaped instead of flat. In fact, that is the optimum design for these rings, but the work is still ongoing. Dental work, I've helped people bond strain gauge to teeth. So for example, you take this tooth and you put it into your Instron test machine, you compress it with a strain gauge based load cell, you get load versus strain. You would then drill the tooth and fill it or do some sort of work to it, and then repeat the test to see how the tooth strength has changed. We also gauge up bridges, plates, bone inserts, that kind of thing. And then if you're unlucky enough to break your bone, then you may need a fixator, and these fixators often are strain gauge as well to optimize the healing process. So fixators have to have a certain amount of flexibility because bones don't heal so much when they're held rigidly. We also stick strain gauge onto joints like knees and hips, and the tools that are used to actually put them in. So we've gauged up bone saws, that kind of thing. Prosthetics, well, most false legs in the past were static, whereas nowadays they've got actuators and force measurement. And as you're probably aware, when you stand still, you're actually continually moving. So modern prosthetics, they will deliberately unbalance the patient, which enables them to actually stand upright, ironically. And then infusion pumps, if you're unlucky enough to have something being pumped into you in hospital, the pumps have strain gauge systems for patient safety reasons. So I've covered a lot of ground, so I just want to cover some additional information, just some resources that you might want to pick up if you want to learn more. Firstly, we do have a website where we have a knowledge base, which is all the tech notes, tech tips, instruction bulletins, how to install, solder, how to compensate for temperature effects, that kind of thing. We do training workshops all over the world, and we have our strain blog, a series of articles. We have a YouTube channel, so plenty of videos to show you how to do various things. And of course, we're members of professional organisations such as BSSM and the Engineering Integrity Society. So really to wrap this up, nearly the final slide, this is simply just a load of keywords that I put together. And if you don't see your own industry in there, let me know. And I will then see where strain gauge is used in it and add it to my keyword list. But you can see many things that we haven't talked about today, like oil and gas, web tension, rocks and concretes, hydroelectric power stations, all the things where I've been personally sticking strain gauge on taking readings. So that brings me to the end, and I think I'm just about on the 45 minutes.
Yes, nicely timed, Anton.
Oh, thank you. Yes. I think I'm okay there, but yeah, so are there any particular questions, anything you'd like me to go back over and perhaps talk about in more detail?
I've not seen it. There are no questions coming up in the chat. Folks, please do feel free to put a quick note in there if you do want to ask a question. We have someone's raised their hand. Navdeep. Hopefully I'm pronounced your name right. You've raised your hand. Please go ahead.
Yes, thank you. Very informative. I joined a little bit late, but I'm glad I still joined because of very good. Can I ask the future of it? So, like you said, it's been going since 1950s and so on. What's the future development? What advancement are we going to see in this measurement technology?
Yeah, that's a very interesting question. It's something actually we were discussing just before we started. And the fact is that through my entire career, I've heard people saying that the foil strain gauge will soon disappear. And yet we're at a point in history where more strain gauges are used, not fewer. Now, there are some people trying to develop printed ink type strain gauges. Vacuum deposited films have been around for quite a long while as well. But currently there seems to be no technology that will replace strain gauges in everything. Even optical techniques just don't have the resolution or sensitivity when we talk about measuring small strain values, whereas for wider range sort of or high elongation measurements, optical can come into its own. But I don't see it really developing further. The advanced sensor technology that I mentioned earlier really is the only change to foil strain gauges that I've seen in my career, certainly. The same backings are used, the same foils are used, the same adhesives are used. The future, who knows? There may be something that can replace it, but I don't see that technology yet.
Thank you.
Great
Okay.
stuff.
If you have something, let me know.
Couple of questions come in. Robert has asked, how long does the bond gauge to metal or gauge to substrate last, typically?
Yeah, I mean, that's an interesting question again, because the MTBF of a strain gauge is often asked, and it's an almost unanswerable question because it's so much dependent on the environment, the skill of the operator, the thing that it's bonded to, the strain levels, that kind of thing. But we have seen through our Vishay Nobel division, who produce systems in very difficult environments, they're now talking about a proven track record MTBF of more than 50 years. So
I think that's reasonable. And Anton, I think we've both probably seen ancient mechanical test machines that were built in the 1960s, and they're still working with their original load cell.
Absolutely,
So
still calibrating
just
as well.
empirically, it's pretty nice as long as you're kind to it.
Yes, that's right. I mean, in fact, to use one of the more sort of difficult environments, I had a customer in Norway who aimed 30-year life in subsea conditions. And that's one of the more difficult situations. They're obviously hermetically sealed, inert gas purged, but 30 years plus under seawater.
I think part of the answer to this kind of comes back to something I did long ago in a past life of dealing with adhesion. And if you put it in a nasty environment, it doesn't matter what you're sticking to what, things attack the bond line.
Exactly, which is why your protective coating is so important.
Yeah. Couple more questions in. What are the hottest and coldest strain measurements you've seen?
All right, okay, so coldest is about -269, so liquid helium temperatures. And in fact, the MBond 610 I mentioned earlier is capable of surviving the thermal shock. So you can actually plunge a strain gauge installation into liquid helium and it won't fall off. The hottest end, conventional foil technology, is around 400 degrees Celsius. But we do have some technologies that are either free filament gauges bonded on with ceramic cement, or we do some weldable high temperature gauge as well. You're looking about 1200 degrees Celsius. So if you're working on exhaust systems or heat exchangers, there are technologies that can cope with that high end as well. But for the bonded foil that we've mainly concentrated on, -269 to +400 short term.
Okay, good stuff. I think there's some fascinating technology out there at the weird and wonderful high temperature end, but
absolutely
not today's topic so much.
No.
Couple of other quick ones, and I'll let you answer this, although I think I know know what the answer is. Can Arduinos or Raspberry Pi systems be used to create simple data acquisition units capable of reading strain gauge outputs?
Yep, absolutely. You've really got two approaches, instrument, and one is buy something dedicated and the other is build your own. Now, the only downside of building your own is many people get it wrong at the front end, and that is the Wheatstone bridge. If you get the Wheatstone bridge right, i.e. using foil resistors for very good thermal stability, and then you use a stable amplifier so you get the voltage output from the Wheatstone bridge to a reasonable level, then of course what you plug in then is merely down to your ingenuity to convert the voltage into the engineering units that you're interested in. And yes, people are using Arduinos and Raspberries and many other custom devices. But if you're using a strain gauge every day in a laboratory, buy an instrument will save you a lot of heartache and, believe it or not, a lot of money as well.
in the long run, yes, I think I think a lot of that technology is very available now. But then when you get down to real high sensitivity and high quality measurements, there are all sorts of other things that both Anton and his colleagues do and my colleagues do when you start looking at the data processing and so on.
There's more in it than you realise, put it that way. But if you get it wrong at the front end, forget the rest. Okay.
Yes. 2 more questions. I'm going to try and squeeze in 2 more. Given the long operation time, do strain gauges need recalibrating? What about use in space environment? I suppose that's to do with very, very high vacuum and low temperature conditions.
Yeah.
Focus on the recalibration and
yeah.
That side
So recalibration. I think generally a strain gauge has a gauge factor for life, and if it remains bonded, it will remain stable and reliable. It can be down to the material it's bonded to, because of course if the material it's bonded to changes, then clearly that will change the apparent calibration. But again, we have anecdotal evidence of load cells being calibrated year on year for more than 50 years, and simply there is no change. It's just that for reasons of traceability, they are recompared and recertified. So essentially you can consider a strain gauge to be, you get it with a gauge factor. That is the gauge factor for life under certain conditions. Gauges do fail if you're using very high cycle fatigue, very high strain levels, that kind of thing. But again, there are products you can choose that will make a gauge last longer at higher strains. Calibration remains essentially constant. I think
the recalibration tends to be more at the transducer level if you've done something unkind to it.
Yes.
A quick clarification there is Mark, who wrote that. His point was space environments can change material properties, which I think is true. Yeah.
So under radiation environments, you would have to be careful about what you choose. So polyamides generally are fairly radiation resistant, but ultimately radiation will attack an installation as they attack and embrittle all materials. So protecting gauges from that radiation environment will be your number 1 priority, but they're used all over space. We have them in vacuum environments. We have strain gauges being used in things like the extra large telescope, which is the European telescope, where these systems have to go into a vacuum regularly for redepositing, and the strain gauge systems are all built to survive that.
Good stuff. I'm afraid we're out of time, but perhaps something that we could maybe pick up on and just put the response back on this. So one other question was that you'd mentioned measuring residual stress and the types of gauges that you'd be using in that context. If it's a long answer, perhaps we'd better take it up by email. But
I would suggest read ASTM E837 and look at the NPL Best Practice Guide number 53. They would be really good starting points for residual stress.
Essentially the NPL one should be free, and you should be able to find it on their website. Unlike the ASTM standard.
Yeah, the ASTM you have to pay for, I'm afraid.
So, good stuff. We are spot on 2 o'clock, so I'm going to say thank you very much, everyone who's asked questions and everyone who's attended. Especially thank you, Anton, for giving us a whirlwind tour of the world of strain gauges and how they're used.
Pleasure. Thank you.
So, and with that, I think we shall say thank you and good night, everyone. And thank you again to Anton.
Thank you for attending and appreciate your questions. Cheers.